Okay, we are going to look at a more complex example in which we're going to do what we did before. We're going to use the same process, but instead of just simply adding a worker to task C, which we saw was not very effective because task B is almost a bottleneck. Like task C is the bottleneck, but task B is not far behind. So as soon as you add a lot of capacity to task C, double its capacity, task B becomes a bottleneck and doesn't give you a lot of gain. So you go from 12 units per hour to 15 units per hour. That's not a huge amount of gain in capacity. So what we can instead do, instead of just adding a worker to task C, is to try to increase capacity with cross-trained workers. So what we do is we say, okay, we're going to add a cross-trained worker so that task B and C together are going to have 3 workers that they can employ. And at any given time, 2 workers could be at task B or 2 workers could be at task C, and one worker switches around to make that possible. And that effectively gives you 5 plus 4, 9 minutes of work needs to be done by 3 people. So that's effectively 3 minutes per unit cycle time, right? And now if you look at our bottleneck, well, tasks B, C, and D are all bottlenecks. They all have the same cycle time and the highest cycle time. And the capacity now will be 60 minutes divided by 3, which would give you 20 units per hour. So going from 12 to 20 units per hour is a much higher boost in capacity than going from 12 to just 15. And so that's the power of using cross-trained workers. Now, doing this in simulation can be a little bit tricky, so I want to walk you through it. Once you see why we are doing a few things, it's not tricky anymore. I think you'll be fine. But I think it's useful to be able to simulate this sort of stuff. So to simulate a cross-trained worker, we'll need to use the resource pool block for the first time. So just drag this block onto your simulation diagram. You set its capacity to 3, so we need 3 workers because this pool will be used by both step B and step C. Okay, so you can't have step B have 1 worker and then pull 1 worker from there. Either step B has to be a delay block with a capacity set to 1 or 2, or it can be a service block which has seize, which can seize a resource and release a resource. And if you're seizing and releasing resources, then you can't have 1 fixed worker and 1 kind of shared worker that you borrow. You have to just borrow both workers or 1 or 2 workers as you need them. Okay, and so we are not going to do this where this 1 worker moves here. We're going to do something equivalent. We're going to have 3 workers in a pool, and task B will get 1 or 2 of those workers at any given moment, and the task C will get 1 or 2 workers at any given moment. Obviously, if task C is using 2 workers, task B will get 1. If task B is using 2, task C will get 1, and that will switch around. Okay, so we create this workers resource pool and we set its capacity to 3. Then we can't have a delay block for step B and C anymore because delay blocks like step A and D cannot seize a resource and then release a resource. The seizing and releasing aspect is built into the service blocks. Or you can use a delay block, but then you have to use a seize block before it and a release block after it. So you have to manually seize and release using seize and release blocks. And that's possible too, but because service block has all that logic built in, all that stuff built in, I don't want to draw 3 blocks, but I can just draw 1 block that does everything. And so I'll just draw a service block for step B and a service block for step C, and I'll specify to pull resources from this workers pool, and I'll specify this has to pull resources from the workers pool too. Okay. And the delay values for step B and C will be the original values of 4 and 5 minutes, because this is the effective cycle time that happens because of the 3rd worker moving around. But we're not going to enter 3 minutes, because if we enter 3 minutes, we're not simulating the cross-trained worker. We're just saying, okay, effectively, this is the equivalent process, right? So you want to simulate the actual, moving of workers between step B and C, and keep them at the original times, because the time needed for this task is 4 minutes. It's just that when 2 workers do it, it's faster, and keep that as 5 minutes. So the delay property of step B is still set to 4 minutes. The delay property of step C is still set to 5 minutes. The only thing that's changed is that now they can seize workers from this workers pool, which has 3 workers in. The capacity of the workers pool has been set to 3. And they don't have any capacity outside of seizing workers. They don't have their own innate capacity to do anything. Okay. Source and sink blocks, make sure the arrival rate is set to higher than the bottleneck capacity. Because we can get a capacity up to 20 units per hour, set the source block like 22, 25 arrivals per hour, anything above the bottleneck capacity, because if your demand is too low, then your output will be restricted by the low demand, not by the bottleneck. So we want to see the bottleneck play its effect and show us how it's affecting the process. If the demand is low, obviously if it's lower than the bottleneck capacity, the bottleneck doesn't matter. The low demand is going to drive the low output. So just set the source to a rate higher than the bottleneck capacity or the process capacity, which is 20 units per hour, or we expect it to be 20 units per hour, so set it above 20. This is just an infinite queue just to capture the demand that's not going to flow in, because we want to keep the demand higher than the bottleneck capacity, just to test the effect of the bottleneck. So this has all been explained before. So the source block, the first queue block, the sink block, they're all the same. Step A, step D are the same as the previous example. It's just an extension of the previous example. The changes are right in the middle here. Step B, step C became service blocks, pulling resources from the workers pool. The workers pool is a resource pool with a capacity of three workers. Now, these are some settings we have to set on step B and step C. So these you may not be familiar with because you haven't used service blocks before. So one thing we can do with service blocks is we're going to say in the C's portion to get units of the same pool, because we have just one pool. In some situations, you could have alternative resources. So let's say if in a hospital, if a nurse is not available, you could in an emergency pull a physician or a physician assistant or somebody else who's a healthcare worker. So you may have a resource pool for nurses, another one for physician assistants, another one for physicians, and you may, if one resource pool is empty, like everybody's is working somewhere else, you can go to the next pool. So then you would do alternative resource sets. Okay, but we don't have that. We just do units of the same pool. You're just going to pull multiple units from the same pool. The pool is workers. This name here must match whatever name you gave to this block. So if you drag the block and you named it my workers, this will say my workers. If you named it, Tom and Jerry, this would say Tom and Jerry. So the name will match. You can just press the drop down button and it will show you all the resource pool on your process map, and you only have one, so just pick one. So that units of the same pool, you pick the workers. Because I told you these service blocks have a built-in queue, you cannot set it to 0. So just put a value of 1 to have like a minimal queue, and that wouldn't affect your capacity at all. It wouldn't really affect your throughput time by much either, because when this is working on something would get queued, but then immediately after that it would block step A. So step A's blocking would start just a tad bit late on the first time, but then once the queue has been filled up, the queue of 1 fills up pretty quickly, then the step A gets blocked all the time anyway. So it just affects your throughput calculation in the first few units that flow through your model until the queue of 1 gets filled, which is like, this queue will take 1 unit to get filled, this will take 1 unit to get filled. So by the time you're in the 5th or 6th unit of the simulation, everything is running properly. Nothing is affecting your timing, but the first 5 or 6 units, like the warm-up phase of the model, the queue size of 1 will take 1 unit more for step A to start getting blocked than otherwise. So it doesn't affect your statistics much at all. So we set it to the lowest queue size because we are not trying to model queues here. We just have this process. Delay time is 4 for step B. See, this is step B as it was the default one. Step B is 4. When you go to step C, this would be 5 right here, the delay time. Okay. And then this is really important. Now, look at this picture here. Task C is the bottleneck. And so the cross-trained worker has to spend more time on task C than task B because task C is the bottleneck. And we cannot tell any logic to split the time of the cross-trained worker in a ratio of 2 to 1. Or all 3 workers in a ratio of 2 to 1, that they should be spending, or a ratio of 5 to 9. They should be spending 5/9 of their time in task C and 4/9 of their time in task B. We can't specify these sorts of ratios. But you can get the same effect by giving priority. So we'll give a higher priority to step C. So whenever both of them want a worker, step C will get it, and step B will get lesser priority. So when and that is fine because step B is faster. So it can always catch up. Step B, C is the slowest step, so you're going to give it higher priority. Okay. Also, what we're going to put in is that the step with the highest priority is not going to take all the workers. So step C is never going to demand all 3 workers. Because if we let step 3 take all 3 workers, then step 2 would only work when step C did not need any worker. But we are only going to allow step C or step B to have a maximum of 2 workers. So when they have a maximum of 2 workers each, the other step is never short of at least 1 worker, because there's 3 total workers in the shared resource pool. So step C has higher priority. It will take 2 workers, and then 1 worker will go to step B. But then when step C does not need workers, after his 5 minutes are up, and this is it's actually, I mean, with 2 workers, every 5 minutes it gets rid of 2 pieces. But then when the queue is empty, because it got rid of 2 pieces, 1 worker will go to step B to try to empty that queue out. Okay. And if your simulation results look kind of funny, you could increase the queue size to 2 units each, because sometimes we do need 2 units queued up, because when you grab 2 workers from the resource pool, we want something there in the queue for them to work on immediately, right? And so, if, for me, I get good results with a queue size of 1. But if you are doing other models with this sort of cross-trained worker sharing, sometimes you may have to set the queue size to be the same as the number of workers you want to grab. Okay, so just keep it in mind. I didn't have any issues with a queue size of 1, so I think it works like that too. But if it's not working as expected, you can increase the queue size to be equal to how many workers you're going to grab, so you have that many units queued up to start working on. Okay, so task priority for step B will be the default value of 0. For step C, you would set this to 1. Any number higher than 0 will prioritize step C. The higher the priority number, the higher the priority that step gets. Now, this property is very important. Number of units. How many resources to pull from the resource pool? How many workers to pull? Okay. And so this looks a little bit tricky, but it's really simple. The question mark, this is this statement right here. Workers are idle. And then you have this open parentheses, close parentheses, greater than 1, then a question mark. Then you get the number 2. So a little bit erased here, unfortunately, but it's 2. You can see right here is 2, colon 1. So what does it mean? Workers is this pool of workers. So if this is called my workers, you would type here my workers. If this is called Tom and Jerry, you'll type here Tom and Jerry. Okay, whatever you call it is the name you have to use here. And the name is shown up here as well. Same name up here, same name here. Dot idle means we're calling a function, a method on our resource pool, asking it to tell us how many idle workers do you have, how many available resources do you have, basically idle resources or the available resources. The parentheses indicate that this will return a value to you. So workers or idle will either evaluate to 0, 1, 2, or 3. There could be 0 idle workers, or 1, or 2, or 3. Okay. If you have more than 1 idle worker available, that's bigger than 1, then question mark means then. So if this is true, if you have more than 1 worker available, then give me 2 workers. Resolve this whole statement to the value 2, which means give me 2 workers. Colon means else. Else, if this was not true, that you have more than 1 idle worker available, then give me 1 worker. Okay. And there'll always be an idle worker available, because this statement never demands more than 2 workers, and we put the same statement in step C. So both step C and step B are never going to demand more than 2 workers, so there'll always be 1 worker left behind. So if step C gets the workers first, step B can still get the 1 worker. If step C gets 2 workers first, step B can get the other worker. So either way, there's going to be 1 worker for the other step. And so that's why we are only demanding 2. If there's 3 workers idle, we're not demanding all 3. Okay, we're just demanding 2 workers. So just type this in as you see it. And if this doesn't make sense, don't worry about it. Just remember that this is a logic statement. What's before the question mark is a logical condition: bigger than, less than, equal to, not equal to, something like that. It's a condition. If the condition is true, you resolve to the value right after the question mark. That's the value to return if it's true. So we resolve to 2, i.e. we demand 2 number of units. If it's false, the condition is false, and you resolve to the else part, which is the value after the colon, the last value, and that's just how you write logical statements in certain computer programs and programming languages. So that's what you would write here. Okay. And then that's it. We're all set up. You set up and you do the same thing for step C. So you go to step C, the units of the same pool, workers, write the same statement. Q is 1, delay time will be 5, and task priority will be 1 for step C. Okay. Your model will look something like this when you run it. And let me show you. So this is our model. So if we run it, you can see we've got almost 2000 output in 100 hours. So 2000 over 100 is 20 units per hour. So we did get the expected capacity. Okay, we're expecting about 20 units, and we did get, there's a typo here. Let me fix that. Okay, so notice I put a 1196 and a 1996. I got 1996 units outputted, so that's the correct one. I made the correction. So the capacity will be about 20 units per hour. And as explained earlier, well, why are we not getting exactly 2000 units out? Because that's what we expect. Because it's random arrival, so the first unit doesn't arrive at time 0, so you don't get the full 100 hours. You get less than 100 hours. Then really the capacity starts, you get 20 units per hour once you hit the bottleneck. Like step B. So first the unit doesn't arrive at time 0, then it spends some time in step A, and then it gets to step B and C. And so really you waste the time in the beginning. And then at the end, some of those units have been processed by the bottleneck, step B and C. They might be stuck in step D. And so because the capacity, the 20 units per hour is really the capacity of the bottleneck, right? And that's running the whole process at that speed. But if the unit stuck in other parts of the process and the first unit doesn't arrive at time 0, then you have to shave off that time out of 100. So if I was to divide it by, 100 hours minus the time before the first unit, at the time at which the first unit arrived, maybe the first unit arrived after 20 minutes. I have to subtract 20 minutes, and I have to subtract the time taken in step A, and I have to add 1 unit that's stuck in step D. Well, step D is also a bottleneck. We have a 3-step bottleneck, but if it was only step C was a bottleneck, then, well, no, actually step C is really the bottleneck. With the cross-trained worker, we are able to support the bottleneck more and kind of bring the effective capacity of the bottleneck up and step B up so that they're effectively the same capacity as D by giving them this shared cross-trained worker. Obviously, because these workers, 3 workers work on step B and C, which are both bottleneck steps, both have the same effective capacity after the cross-trained worker. They're going to have 100% utilization. Again, why do they have 99% utilization? Because the simulator, if you get 99.999, it's just going to show you 99%. Okay, it's not going to show you 100. It's not going to round up to 100. And why do you have 99.99? Because the workers are idle until the first unit arrives, passes through step A, and gets to step B. So maybe the first unit arrives after 15-20 minutes, then gets to step A. By the time it gets to step B, these 3 workers were idle for the first 30 minutes of the 100 hours of simulation. And so that is why you get 99%, not 100, because of this warm-up period. If you started collecting statistics after the warm-up period, then you wouldn't get this small variation of the expected answer. Okay. Now, this is a really cool example. It's a process with parallel steps. So we saw, you might have seen this process. I used this example in my lecture on process analysis. So it's like a loan process. You get a loan application. Step 1 takes 10 minutes. Step 2 takes 20 minutes. But because step 2 is the bottleneck, we added 2 workers to increase the capacity, because otherwise the capacity would be 60 over 20 or 3 loan applications per hour. That was too low. So we added another worker on step 2. Step 2 has 2 workers. Everybody else has 1 worker. And so because you could do every 20 minutes, you could do 2 loan applications through step 2, then the effective cycle time of step 2 is going to be 10 minutes. So step 2 is no longer the bottleneck. And then we have 2 steps in parallel, step 3 and 4. When both steps are complete, step 5 can start on that particular loan application. Okay, and so step 3 is a bottleneck 15 minutes, and so the expected process capacity is going to be 60 over 15 minutes or 4 loan applications per hour. Okay, but how do we do these things in parallel, and how do we tell AnyLogic not to just start step 5 if step 3 is done, but to actually wait for step 4? Because if our agent comes in, flows here, first of all, our agent doesn't know where to go. We have just one agent per loan application. So if it goes up, step 4 doesn't get done. If it goes down, step 3 doesn't get done. So we somehow have to split our agent so both step 3 and 4 get done. And then you have to combine those two parts together and then do step 5 when both of the parts are available out of step 3 and 4. So we actually do have blocks to do that called the split block and the combine block in AnyLogic. So in a split block, an agent flows in through this input port, the green port on the left, and the same agent goes out of the green port on the right. That's the output port, and then the bottom is the output copy port where a copy of the agent got out from here. So you got one agent in, it got copied into two agents, and they can go on different parallel paths. Okay, because they're basically the same loan application. One emailed copy or electronic copy or a shared Google Drive version goes to person A to look at, and the other copy goes to person B to look at, but they're really the same loan application. So because we copied our agents, create a copy of our agent, for every one agent, we got two agents out here. We need to combine them back. Otherwise, if 10 agents came in, we'll think we have done 20 loan applications because 20 agents would go out. So if whenever you split an agent into two, like make two copies or make one copy and one original, so you get two out of one, you have to combine it back so that you don't have a demand of 10 output of 20. That doesn't make sense, right? Are you creating loan applications by yourself? So if you split, you have to follow by combined block somewhere. So what the combined block will do is it'll let two input ports, so two things will come in. So the original agent from here and the copy of that agent, they will go through some different paths and eventually hit the combined block here and here. And then the combined block will combine them into one agent. And there's multiple logics. Either you can just pick one or two, or you can create a new copy based on some version of both of them. You can specify some complex logic, but usually I just take the original here and just discard the bottom one. So there's a setting here where you can say, okay, just take agent one, which is the one here, or you can say just create a new copy, destroy both of them and just create a new copy. Why would you want to create a new copy and destroy both of them? What if both of them had different information? So in more complex simulations, you can add data to the agents that are flowing through the system. Like somebody could make comments on a loan application, right? So you could add notes on a loan application original and notes on the copy of the loan application by another person. And then when they come to combine, you could write some code or some logic to combine the notes into a big mega list of notes and attach it to a new copy of the agent and just discard the old copies. So you kind of squash them or combine them into a new agent with the notes from both combined. But we don't have to do any of that for us. We're not keeping track of any note, any changes to the application. We're just doing a high level process simulation. So we can just take this agent, let it go out here. Any option you pick, take agent one, agent two, or make a new copy, will give you the same results because they're identical. There's no change in the information they carry for us. Okay. The key part for combined block is it waits for two agents to arrive. So if, let's say, this goes through path A, this goes through path B, path A is faster. If an agent arrives here quickly from path A, it's not going to just send it out. It's going to wait until an agent arrives from path B. So when both path A and path B finish, then it's going to send it out, which is exactly what we want. We want step 3 and step 4 to both finish, and step 4 is faster. So we want the combined block to make the agent from here, step 4, wait, and then when step 3 agent comes, then send one agent to step 5. Okay, so this is what the process diagram looks like. Okay, these are just delay blocks, simple delay blocks you've been seeing, source and sink blocks. Because our capacity expected is 4 loan applications per hour, make sure you set the source to some number higher than 4 units per hour arrival so that you're not demand limited, because you want to check the capacity, how the bottleneck is affecting our output. We are not trying to see what happens when demand is very low. If you are wanting to see that, you could obviously do that, but that's not the purpose here. So you set the capacity something above 4, like 8, whatever, 10, 7. Doesn't matter as long as it's above the bottleneck capacity. Then step 1 is just a delay block with a delay of 10 minutes. Step 2 is a delay block with a delay of 20 minutes, but a capacity of 2. Remember, delay block capacity is the number of workers at the delay block. So you just set the capacity of delay block to 2 and the delay to 20 minutes here. and then you have a split block, and then you draw these nice lines to go to step 3, step 4, then you have the combined block, and then you have step 5. So I'm just going to show you how to draw these lines and how the split and combined blocks look in the AnyLogic simulation. So let me first show you step B. Okay, step B, notice, no, this is not the right model. I'm working on this model. So let's look at this. This is the model you want to work on, the parallel model. Okay, so step 2, notice has a capacity of 2. It has 2 workers and a delay time of 20 minutes. That was a cycle time, okay? Then you have the split block, okay? And everything is default. Nothing you need to change, just connect the lines. And how do you draw this bent line? Let me show you. Let me delete that. So you basically double click here, and then you can draw a line anywhere. So you go up, and when you have to turn, just click once, and now you can turn. And when you get, okay, I went up a little bit, so I'm going to start again. So let me undo that. So I'm going to double click, go up to here, click once, and then notice if you want to end the line here, you have to double click to end the line outside a port, but that's not recommended. You don't want to end a line here. That'll just be not connect the two things. So, but when you go to the green port, you only have to click once to end the line. Just click once and it draws the line. So whenever you're ending the line at a green port, click once to end. But if you're outside a port, clicking once will allow you to turn the line. So that's how you add these connectors, okay? And step 3 is just a simple delay block with the delay time of 15 minutes, step 4 delay time of 12 minutes, step 5 delay time of 10 minutes. All of them have a capacity of 1 because just 1 worker. This was the only one with 2 workers. And then you can run the simulation and you should be getting, 4 workers out, 4 units out, 4 loan applications out per hour, or close to 400 out after a simulation of 100 hours. So remember, in projects under simulation main, this is where you set real time, stop at specified time, this option, and then you set it to 100 hours, right, to run for 100 hours, okay? Okay, so let's run this model. That's the wrong model selected. Let me close the cross-train model so it runs the correct model. Okay, so you can see that they're going here, and you can see it waits to output. It waits for both of them to come before it outputs them. We can just fast forward, and we can see we got 396 loan applications done over 100 hours. That's about 4 applications per hour. Again, the warm-up time issue, because the first loan application does not arrive at time 0, so we actually get less than 100 hours to work on them. So that's why we don't get exactly 400. So everything is working as expected. So now you actually know how to simulate processes which have these parallel steps. So that is really cool. And that is where hopefully after this video you feel more confident doing simulations, because remember we did cross-trained workers where some cross-trained workers or a resource pool of workers can work on multiple steps. You know how to do parallel processing, right? You've previously seen how to increase capacity by using a delay block with a higher capacity to add more workers, or using resource pool. So with these examples, you have the basics to be able to simulate a lot of realistic processes using AnyLogic.